Okay, guys. Well, welcome to Module 5, right? Oh, and there's Ben. Yay. Okay.
Hi.
Hi. So, welcome to Module 5. So, technically, this class is about 10 weeks long. So, we're well more than halfway, right? Because the last week, I think, is the final. Anyway, good job hanging in there. Keep up the really good work. Uh, Next week, we're going to cover Module 6, which is shelf life. And I'm going to do talk about some more testing things then as we move through. Shelf life is something that I'm sure that most of you know a lot about. And so I don't see why I should talk about that. So what I've done is, because this module is so big, I've divided it up. And so I'll be talking about it again next week. And and then also in module 7, when we talk about microbiology, then we'll talk about the testing, the microbiological testing. So just kind of to spread it out a little bit so it's more interesting. Um, Let's see what else. Notice that in this module, in case you happen to skip around, that there are some extra pages. So be sure you take some time to look at that. I'm not sure that the textbook itself does a really good job of covering testing. There doesn't seem to be any place where it's all in one place. So I kind of created a few pages with some videos in it of some testing equipment, and so be sure to spend some time looking at those pages because I worked hard on those pages. So look at them. Let's see what else. Oh, well, last year, somebody asked me about acidulants versus acid. So acidulant is something that you add to it to make it sour or acid, while the acid is what's being added. So I just put some definitions in there. So, the learning objective that we're going to cover today is to identify common analytical equipment and fundamental testing procedures. And we're going to look at water activity, pH, and bricks and moisture today. So that's what we're going to do today. But I thought before we started, since you guys had such a good time playing with your pens, that it might be fun to go over a few terms and just do a little brainstorming before I get started. So I thought we'd start with carbohydrates. Okay, carbohydrates. And I want you to let's see if I can do it this way better. I want you to draw a line using your pen. So, for instance, carbohydrates, mono and disaccharides. Just do the carbohydrates. So, which of these terms are associated with carbohydrate? So, use your pen to draw a line. Okay. Some more. That's right. Starch and fiber. Okay. Starch and fiber. The Maillard reaction. We've got that one. Okay. What else? There's a couple more. Caramelization. Very good. Caramelization. Right. Make sure. Okay, there's one other. Don't forget water activity, right? Sugars affect water activity, and we're going to be talking about that today. Okay, so any questions about any of those? Remember that caramelization, the difference between caramelization and the Maillard reaction is that caramelization is just like the breakdown of sugars, like if you're going to make brittle. So you just put the sugar in there and you cook it and it turns brown. That's caramelization. While the Maillard reaction is a non-enzymatic browning between proteins and sugars. Okay, any questions? All right, how about lipids? Which of these terms have to do with lipids? Insoluble in water, polyunsaturated, monounsaturated, fatty acids, linoleic and linolenic. All right, I think that's all of them, unless I missed one. So draw a circle around it. Which one is an omega-3 fish oil, linoleic or linolenic? That's right, linolenic. Gone fishing, right? It's got an extra N in it. Great, okay. Any, oh, there it comes back again. Any questions about any of those? All right, here we go. All right. So now let's talk about proteins. Which ones of these have to do with proteins? Enzymes, yes, very nice. Denaturization, yes. Nitrogen, yes. Amino acids, yes. Oh, somebody figured out how to draw a straight line. Buffers, yes. The Maillard reaction, we can count that one, right? Maillard reaction, good, John. Okay, there's one more. That's it, right. Enzymatic browning, right? Remember that enzymes are proteins. And I really want to drill that into your mind that enzymes are proteins. So that way that anything that denatures a protein will also denature and control an enzyme. So you don't have to learn two different sets of values, but just know that enzymes are proteins, right? So that if you add heat, you could destroy the enzyme, or you could denature and coagulate the protein. So that it's all the same. So denaturization is the uncurling. Denaturization is the uncurling, and coagulation is the curdling. Okay. Anybody have any questions about any of that?
Yeah, Jill, I got a question.
Uh-huh.
Regarding proteins, can you have enzymatic browning and Maillard reaction at the same time?
I don't think so because Maillard reaction requires heat. You could have enzymatic browning and then cook it.
Yeah,
And
no,
have,
that's a fair point. That you answered my question. Thank you.
okay, good. Right. If enough heat for the Maillard reaction would denature the enzyme before browning occurred. So, good question though. Anybody else? Okay, well, that was kind of fun, huh? Right? There we go. A little something, a little extra. I'm trying to make it more participatory. Okay, here we go. So I want to start with water because water in food is probably one of the most important elements, right? The water in food. So it's probably one of the most important elements. So the water in food can be in three different ways. Okay, it can be free water. And free water, really a good way to think about free water is that like a sponge, if you squish it out, water that comes out, that's free water. And whatever you can squeeze out, or if you press it or cut it, that water is free. And of course, it's available for microorganisms. bound water that's part of a chemical reaction. So if you remember, we talked about the triglycerides and we talked about hydrolysis and condensation coming together and one molecule being extracted or added. That kind of water that's in a chemical is bound either that way or a polar reaction like sugars or pectins and proteins and ionic groups. That's bound water. So that water is not available. And then entrapped water, which would be things that would be entrapped inside of a starch or a pectin gel. And we talked about that when we talked about amylose and amylopectin and how amylopectin is branched. And so there was a lot of space in there for the water molecules to collect. And so that's why we could get a firm gel. So those are the three different places that we can find water. So the easiest way to measure water is total moisture content. And that is quite easy, right? So, and it will give you the bound water and the free water. So total moisture content. So this word here, quantitative, do you know what quantitative means? Anybody want to volunteer?
I mean, I presume that quantitative is meaning that it can be calculated or derived in a sum or a number.
Yes, right. Absolutely. So, yeah. So, quantitative amount of water. In other words, if we dry it and we measure how much it weighed before and after, then that's a quantity. That's a quantitative, right? So, that's an objective analysis versus a sensory analysis. It's an objective. We get a number, right? So there's lots of reasons that we should measure the moisture content in our food. One of the most is legal and labeling requirements. So the standard of identity of certain foods or the labeling, if you say, how much water you have in your product. Or the list of ingredients is in descending order by weight. So legal and labeling requirements will make it, so if we have very too much, right? So that can be a reason to measure total moisture content. Economic, water's cheap, but expensive to ship because it's heavy. So economic in, how much water do you want to put in there, right? So it's cheap to add, but it's expensive to ship. Microbial stability. If you're worried about microorganisms growing in the food, so that depends on the free water content. So we're concerned about microbial stability. Will it spoil quickly, right? The food quality, texture, taste, appearance, and stability of the food depend on the amount of water that's there. The less water, the spongier, the crisper the texture is going to be. Taste is requires water. So if it's too dry, we don't taste it as much. Appearance, what it looks like. Food processing operations. So if you mix dry or flow through a pipe, the amount of water that's there, how thick it is going to make a difference. So total moisture is important for quality control and efficient use of raw materials. So I'm sure you guys are familiar with some of that. So the common way, the common way is oven drying. So in oven drying, you weigh the sample before you put it in the oven, you close it, you dry it, and then you weigh the sample afterwards and the water that's evaporated. And so that gives you the moisture content, right? The difference in weight. So the moisture content equals the weight minus the weight of the sample divided by the weight times 100, and that'll give you a percentage. Same calculation we use for lots and lots of other things. There are some high-end moisture ways to calculate it. There's a microwave moisture analyzer and a bunch of these ones right here. So any of you, do you measure the moisture content in any of your foods?
Yeah, water is a big topic of discussion in our industry, and I think there's somebody in this group that works for Nestle, so that they'd understand as well in the bases and concentrates and sauces space. There's a constant evaluation of what water is necessary to achieve the final product because, like you said, shipping weight and shipping costs, cost of final goods, and then also it can be determined as ready to eat versus ready to use versus how it needs to be held to mitigate the elevated levels of water activity.
Yeah, right. So yeah. So yeah, so it's really important. So I'm sure you guys do some. And what method do they use to measure the moisture content?
Well, that's where I just walk into the lab and ask them, how's it looking? You know, but I've seen all the tools on the counter. I just couldn't tell you, Jill, to be honest with you. That's probably outside of my scope, but I'm sure we're going to talk about it here. They do use a moisture analyzer. Um, they
You should go.
use a,
Yeah, yeah,
yeah, I've spent some time in the lab with them. They use a microwave moisture analyzer. That is the tool that they use. Uh,
probably true. Yeah,
yeah, that is correct. Yeah.
yeah, because it's fast, right?
Right.
Because this other
Yes.
one, oven drying, takes from 8 to 16 hours. So
No, yeah, this was done in I think 3 minutes and 30 seconds or something like that.
perfect, perfect. Yeah. Okay. So so we talked about total moisture. That's how much moisture is in there. But oftentimes we are not that concerned about the moisture. But if we're talking about food safety, we're really talking about water activity. So not all of that water is available for microorganisms to use, right? So we can measure the water activity or the active water, the water that's available for microorganisms. So the water activity is the relative escaping tendency of water from a food compared to the behavior of pure water. So if we have this on my little picture down here, right? Pictorial definition of water activity. Here's the water in food. So we know that if you have a cup of water and if you leave it long enough, eventually all the water evaporates, right? So the water molecules inside are always moving around and they bump up against the top and eventually they will escape. So that is considered one, the water activity of pure water. Well, in food, the water escapes too, and we know that too because things dry out if you leave them out on the counter. So water activity is a comparison of these two. The escaping ability of the water molecules from the food compared to the water in pure water. So that's the definition. So free water can act as a solvent, right? Can participate in chemical reactions, is required for enzyme activity, and most importantly, participate in biological reactions. So, like spoilage and pathogenic microorganisms. The higher the water activity, the more likely the food will spoil. If you want the technical definition, it's the equilibrium, which means the equilibrium partial vapor pressure of water to the equilibrium partial vapor pressure of liquid water, pure water, at the same temperature. Questions about that?
Jill, I do have one question for you. In the homework, there was a question that asked equilibrium partial vapor pressure can also be described as, and I read that page 35, 36 up and down, and I didn't find a dead giveaway, and I wasn't sure if there was a phrase or some kind of technical term that could also be described as.
I think it's the escaping tendency of water.
Okay, cool. Thank
Nothing,
you.
nothing all that, you know, I think up here, the escaping tendency of water. I'm not exactly sure what I was looking for. And you're
Okay.
right. I always try and put a dead giveaway in there so you know when you found the answer.
Yeah. I couldn't find it. So I was like, oh boy, I actually have to give my own opinion here.
Yeah,
So
yeah.
anyway,
Oh no.
thank you.
No,
Yeah.
no.
All
And
right. Thank you.
equilibrium means, when you leave it there long enough, right?
Right.
So over time, right? So
Okay.
yeah, good question. Sorry about that. So in order to measure water activity, what we do is we measure the relative humidity. So if you have a water activity meter, I think I have one down here. No, I do not. All right, sorry. You dizzy yet? So a water activity meter has, and there's one on the pages, but what it has is it's a little place where you put the food, and then above there is a mirror. And when you close it up, it measures the moisture how the water's escaping, and it compares that to pure water. So they are temperature sensitive, but what they're doing is they're measuring the condensation on this little mirror. So that's kind of how they work. There are a lot of handheld ones, and then there's a lot of benchtop ones as well, but they all kind of work like that. So why measure water activity? Because the higher the water activity, the more mobile the water and the faster it can diffuse within a food or escape from it entirely. Okay, so just looking at a few examples right here, total moisture content and water activity do not directly correlate. You would think the more moisture, the higher the water activity. Yeah, sometimes, but they do not always directly coordinate. So I picked up some examples so we can think about soy sauce, which we know is high in salt. And salt, the ionic bonds the water so that it's not available to escape. So if we look at the total moisture for soy sauce, it's about 70% water, but the water activity is about 0.86. So that's the water activity. So it's high moisture, right? And high salt, but a lower than you would think water activity. But if we look at bread right here, we look at bread. Bread has a total moisture content, and we think of it as being pretty dry, of 35%. But it has a high water activity because all that water that there is available for for microbial growth, etc. So peanut butter, which has hardly any water, has a relatively high water activity. So does dry milk. Can anybody guess what is the difference? Why is there a difference in the water activity between regular preserves and sugar-free preserves?
Because of sucrose versus whatever it is that they use, I guess some form of fructose or natural derived plant derived sweetener,
Artificial sweeteners.
artificial sweetener, right?
Yeah, artificial sweetener. Right, right.
Hmm.
So you can see that the amount of sugar has an effect, a big effect, because
Hmm.
the water is bound to the sugar molecules,
Right.
right? So it has a big effect on the water activity. So two things are important. If we look at the dietary guidelines or the FDA or whatever those crazy people are up there, they're I'm sorry, I didn't mean to mention politics. If if they want us to lower the salt content and to lower the sugar content in food. And that is going to dramatically affect the water activity. So it's very important that we either add something like that's, an additive that's going to discourage the microbial growth, or that we're aware of what's happening and that we treat the food in a way that, because it's going to be riskier. Right? Does that make sense? So, a potentially hazardous food, or whatever we call them these days, what is it? Something for safety, right? Has a water activity of 0.85. And there are not a lot of numbers that you need to know, but this is a big one, right? So you need to know the water activity. Put that on a flashcard someplace. It's because this is the regulation guideline. So a food that has a water activity greater than 0.85, we have to control the bacteria, the pathogens in another way.
Jill, I'm surprised to see soy sauce does not meet that criteria just because I mean the amount of salt that's in the soy sauce. Is that why you tend to see gluten or wheat? Does the wheat create some kind of barrier? I'm confused as to where that, you know, how that's mitigated. I mean, what do you do with soy sauce when it's
Well,
when it's
technically, I understand you're supposed to keep it in the refrigerator after you open it.
oh, is that what it is? So that's where that application on the back of a bottle says
I mean,
refrigerate after opening.
most of us don't, but
Mhm.
technically, the recommendation is to refrigerate after opening.
That's crazy to think that every bottle of soy sauce sitting out on a shelf somewhere is a petri dish for
Now,
pathogens. That's
it's so
crazy.
really close, and in a minute, when we look at this moisture absorption isotherm, you're going to see that that it's probably not that risky, but yeah, that's the guideline.
Okay, cool. Thank you.
Yeah, yeah, but it's a good question, right? You would think that it would be lower because of the amount of salt. Uh, so now we're going to look at a chart. It's called the moisture sorption isotherm. And essentially what it's going to do is it's going to measure the moisture content and the water activity, and how those, how the risk and how things change over time. So it compares water activity to moisture content. A couple of just a brief, the learning objectives say adsorption, I think, but just a reminder, absorption is giving up and adsorption is reclaiming, but the two words are used quite interchangeably, so they're kind of considered the same process. One is giving up, and so I don't think you need to know the difference, but it does show up in the learning objective. So water activity, stability diagram. So this is a really, really cool chart that I tend to use a lot. So you've probably seen it before, but this side here has moisture content and this side here has water activity. Okay, so if we look here at this, the isotherm, this dark line right here. As the water activity is really low, like in a lipid, right? Because there's no water in lipids, we see that there's a lot of lipid oxidation because the oxygen can get to the lipids really, really easy. So things that have really low water activity are likely for lipid oxidation or rancidity. So if we look at that one. If we go to the other extreme, something that has a high moisture content and a high water activity, then we see a lot of biological activity, mold growth, bacteria, yeast, enzyme activity, right? So the more water we have. So between in here, we have a loss of crispness and powder caking, right? And then once we get here, we see the more water there is, the increase in enzyme activity, mold growth, yeast, and bacteria. So when I said before that the potential had as food, we said it's 0.85. This looks a little high right here, but that's where they drew the line. 0.85 was the magic number. So you can see that bacteria don't start to grow until quite a little bit higher than that. So while you might get yeast and mold growth in your soy sauce, you're not likely to get any bacteria to grow in there. So it's not likely to make you sick. So yeast and molds make things taste bad, but they don't make you sick. Questions about this? If you look at it, it seems quite logical, but not always. Any questions? Okay, another thing to look at is that browning reactions, like the Maillard reaction and the enzymatic browning, occur right here in the middle when there's a lot of moisture, right, in the middle. Enzyme activity, see what happens to the enzymes as the water activity increases. Hearing nothing from student land, I will move on. So just a couple of things to think about. Water activity is temperature sensitive. And again, potentially hazardous foods has a water activity above 0.85, and that's in the Code of Federal Regulations. You do not need to know the numbers of where it shows up, but it's there. And all of this is just what I talked about before. Any questions about water activity and moisture content? It's a really, really important concept that you understand the difference, right? Really important. Because while moisture content can be really high, if the water activity is low, then you don't have to worry about bacteria and yeast and molds. But if the moisture content is low, but the water activity is high, then you have to worry, right? Especially when it comes to food safety. Okay. All right. Now let's talk a little bit about acid versus pH and titration, which I think I changed the name of this when I was reviewing my notes one last time before class. So we know, so there's two different ways to measure the amount of acid in a food. One is pH and the other is titration. What is the difference and why is there a difference, right? So pH versus titration. So first of all, we need to understand what an acid and a base are. So an acid is something that has a lot of positive hydrogen ions. Remember, we said that the hydrogen can give up the hydrogen is normally neutral. It has one proton and one electron, going way back to the beginning of class. But when it reacts with this oxygen over here, the oxygen is really big and a hog, and it can steal the electron. So what happens is that the hydrogen now has a positive charge because it's missing an electron. And the OH over here, the oxygen and hydrogen, has a negative charge because it has one extra electron. So the balance of those in the solution tells us whether it's an acid or a base. Acids have lots of positive charges, and bases have lots of negative charges. So why is that important, right? So that's important when we measure pH, because pH actually measures the difference in the electrical charge. So it has a reference electrode, and a reference electrode, and then the electrode, the glass thing that goes in your solution, the glass thing that goes in there, that measures the positive and negative charges. And if there's more positive charges, it's going to be acid. And if there's more negative charges, it's going to be a base. All right, so that's what a pH meter measures. So it only measures the electrical charge. Questions about that? Nope. Okay. I can see Brian up there shaking his head. Nope. Okay. Right. I think I put Ben to sleep. Did I put you to sleep down there, Ben? Okay. That's the only people I can see. Everybody else is hiding. So I think you know what things are acid. Oh, there you are. Hi, Daniel. So I think you know what things are acid and what things are base. Just know that the pH scale is based on 10 times. So it's logarithmic, like the Richter scale. It's logarithmic. So every going up one is 10 times greater than the next. Adds another zero. You can think about it that way. Most everything we eat falls right in this area, right, down in here too much. Okay, so that's kind of this. So that is pH. A couple of things to remember if you get asked to use the pH meter. One is they need to be calibrated regularly. So they come with a calibration solution. They should be calibrated regularly, daily, if not more often than by shift. So because they drift. So they should be calibrated regularly. The electrodes are fragile. They're glass, so they're not a stirring rod, right? So be careful with them, because once they're disturbed, they no longer measure correctly. They also have a shelf life. They don't last forever. They need to be replaced on a regular basis. pH readings are temperature sensitive, so it's very important that the temperature of your solutions that you're comparing, your foods that you're comparing, is always the same. They should never be stored in distilled water, so we store them in electrode solution or regular tap water. And they should be cleaned well after each use, based on the manufacturer's recommendation. So it should be asked to work the pH meter. That's some important things to think about. So the federal regulations, there are several different kinds of foods that maintain based on the pH. Low acid canned foods. This one always drives me crazy. Low acid means it's not very acid, means it's more neutral. I don't know whoever came up with that name, low acid. Low acid always makes me think it's very acidic, but it's not. It's not very acidic. I guess you could say it's not very acidic. So they have a finished equilibrium pH greater than 4.6. So before I said the water activity number you needed to know is 0.85. The pH number you need to know is 4.6. So these are both federally regulated. So low acid canned foods. An example is canned green beans, canned spinach, canned things that are canned that are not acidic. An acidified food is a low acid food that has acid added, pickles. right? Anything that's pickled or fermented. A potentially hazardous food has a pH greater than 4.6 and a water activity greater than 0.85 and contains proteins. This should be pickled vegetables and pickled eggs. Not just eggs, pickled eggs, right? So those are 3 federal regulations. Later on in the class, we're going to discuss retorting, and retorting has to do with low acid canned foods. Okay, so we're going to talk about that, all the rules about retorting. So that's why you measure pH. But pH doesn't give you all of the acid that's in the food, because some of the acid doesn't disassociate very readily. So there are 2 kinds of acid. There are the inorganic acids. So if I put hydrochloric acid in a solution, the hydrogens break off from the chlorines pretty much right away. Poof, all 100%. Poof, you put it in water. Same with battery acid or nitric acid, right? Those are inorganic acids. We don't work with inorganic acids. We don't put those in food. So that the acid that we use in food is an organic acid, meaning organic, meaning it contains carbon, right? So what happens with the organic acid? And we've been designating it like this, right? An organic acid. So it disassociates, but it doesn't disassociate totally. So when I put like vinegar in the water, it gets acidic, but it doesn't, not all of the acid disassociates. So if we want to measure the total amount of acid, and the total amount of acid is what makes the food taste sour. That's what it tastes sour, right? Is the total amount of acid. So if you're concerned about how sour it tastes, then you want to measure that. So there's only really one way to measure that, and we do that with titration. And titration is really quite simple. So if you put the acid in the bottom and a base in the top, you add base until the solution reaches a pH of 7. And then you measure how much base you put in. You measure that. Usually we put in there's phenolphthalein. Phenolphthalein turns purple at a pH of 7. But a better way to do that is to put your pH meter in there and read your pH meter. It's more accurate than that. That's titration. So titration will give you the total amount of acid, which is a better test for how sour your food is. Questions about the difference between pH and titration? So your labs probably do both, right? So the titration is this big long thing, though I think they do it by machine now, but probably not like we did. But that's what it's doing. That's what the machine is doing. Any questions, comments? Any of you do they measure this in your lab? Not as you know of, right? Okay. All right, well, hearing no comments, let's move on. So measuring sugar. So I'm going to measure sugar. There are 2 ways to measure sugar, of course, right? One is the hydrometer. And a hydrometer is just something that it's a weighted tube, this tube right here. It's got a weight at the bottom of it and measuring thing, across the little gradations across the top. These things right here. So you have a long cylinder and you fill it up and you drop that in, and then you measure the water level, and that'll give you the amount of sugar or salt or alcohol, right? So depending on which one you're using, you have to be sure to use the right thing, the right hydrometer. You have to be sure to use the right one, and it's dependent on the concentration of the solution and how much sugar is present there. But essentially what it's doing, it's measuring how dense the solution is, right? So that's a hydrometer. That one's called a hydrometer. But most of us don't do that. It requires a lot of sample. And so most people don't do that. Well, most of the time we use a refractometer. So a refractometer bases on refraction. So when you have a sugar solution and you put light through the solution, it bends the light. And a refractometer measures the refraction. So looking at, these are the old kind, these are the new kind, right? Refract. And the water activity meter doesn't look a little kind of like that, right? So the light goes in, right? And it's refracted. So then it's measured in the eyepiece. You can see you can see it. There's kind of a line. And
Yeah, Joe, fun fact, when I was taught to make ramen broth, specifically like tonkatsu ramen, higher fat, longer cook time, I was taught to test it with a refractometer, but I was taught, because the person was not a scientist, to use it just to check the density, but it wasn't correlated to the sugar content. I was just taught to see where it lines up. And that's funny to look back on it. Be like, man, we weren't even applying sugar to get a real accurate result. But
yeah.
yeah, it's funny how people use tools and they really don't even know what they're doing with it. But we use both of these in our lab, by the way, in case you're going to ask that question in a moment.
Sure. Yeah. Yeah.
Yeah.
Yeah. Yeah. Yeah. Both are helpful, right?
Yeah.
Yeah. Yeah. And your answer, that's really interesting. So you might have been measuring the salt content.
Yeah, I think that's more so what was happening, because
Yeah.
we were checking basically how viscous, how concentrated the broth was getting to avoid it getting too strong in flavor,
Mhm.
because we would push the emulsification of all these bones and fat for like 20 to 22 hours. And so, yeah, that's more so what we were looking for. And we
Right.
were just going for consistency and the density of the fluid itself.
Right. Which might measure the salt content. So there might
Right.
be a refractometer specifically for salt.
Oh, I suppose that could have been it.
I
That's
don't
just,
know the answer
I
to
don't think
that.
so. Yeah,
Yeah. Yeah, yeah, yeah. Obviously, the guy was doing what he was told, but he didn't understand why.
right.
Right. Yeah. And you were doing what you were told because you didn't have to understand why.
Yeah, yeah, correct. Yeah,
Right,
exactly.
right. So, so when you measure sugar, it's measuring in bricks, and bricks is a percentage by weight of sucrose, table sugar. And these things are dependent. So if you have a low level of sugar amount, you use one refractometer, while there's a different one. I think there are 3 different levels depending on the concentration of sugar that you're measuring. So be sure to get the right ones. It's about the wrong ones for my lab. I can tell you that from right. So, but they're used to measure a lot of different sugar, like you could use it for high fructose corn syrup or honey, but technically it's just a sugar. Yeah. Again, it's influenced by temperature, so be sure that you're using the same temperature, that it's temperature dependent. Okay. Always use the right solution. There similar methods for salt and alcohol. So there you go. Pretty sure you were measuring the salt concentration. So questions? I think these last two, this sugar, are pretty common, right? So density, the hydrometer is measuring the density of your liquid. The more dense it's going to be, the higher it's going to sit, while the less dense, the lower it's going to sit. Questions about any of this? Did it help you understand a little bit about how these things work? That was my goal, right?
Yes.
Yes. Thank you, Daniel. Thank you, John. Right? Cool. My goal was to explain how they work. So let me stop the recording. Great. Let me shoot this. Somebody showed up. I guess not. Okay. I know that Oleg's working in the lab. He told me that. Okay. Questions? Comments?
Jill, just to recap one more time too, so I don't forget this, because I know we went over it and it seemed pretty clear at the time, but the difference between titration and pH is that pH is checking for the electrical charge of the solution, not the definitive acidity. And titration is testing the amount of acid by volume present inside of the solution, right?
Yeah, titration.
Titration. Okay.
Titration. I'm going.
Yeah. Titration. Yeah.
Yes, titration is the volume, yeah, and is used for organic acids,
Okay.
right?
Got it.
And pH is measuring the electrical charge of the
Okay.
solution. Right. So if you want to know the total acid, you have to do a titration, right?
Okay.
So
They're
yeah,
different because titration can be used on organic and inorganic acids, and it's just testing the amount that's inside of the solution
right. And
by volume.
organic acids do not dissociate as readily as inorganic acids. They contain the carbon, right? So they
Okay.
don't dissociate. So and that's, so they're not going to affect the electrical, the electrical transmission. You can measure the pH, right? pH will give you the pH will give you the acid content. But if you want to know the total acid, so pH is really good for regulatory, right? So all the regulatory stuff is based on pH. But if you want to know how sour it tastes, right? If you want to know the
Hmm.
total amount of acid that's there, if you have something that's sour and you want to know the total amount of acid that's there, then you have to use a titration.
Okay.
Yeah, because it doesn't measure the organic acids. So good to ask, Daniel. Good to ask, right? Because they're slightly different. They look the same, but they're slightly different.
Right.
Right?